Okay, today we're going to talk about the 6 types of chemical reactions. And I'm going to abbreviate reactions by RxNS, which is a common abbreviation. All right. I've given the class a couple of sheets that I may refer to periodically in this video. This is the 6 types, and it's going to be some examples also. And then the types of reactions lab that we'll do this week. All right, so have that handy as we go through the notes. All right, there's no particular order. I can approach it in any order. So I'm just going to go in the order that's on this sheet. All right. Okay, let's look at combustion first. Combustion. What you want to be able to do is look at any chemical reaction and classify it and say, oh, this is a combustion reaction. This one is a single displacement. This one's a decomposition. All right, the best thing to do is to look for clues. All right, so combustion uses oxygen as a reactant. All right, so oxygen is a reactant, means it's to the left of the yield sign, the arrow. All right, and carbon dioxide and water are the products. Okay, so that would tell you, oh, that's a combustion reaction. Okay, I'm going to slide this back a little bit. All right, am I still in the view? All right, so that's a dead giveaway. Oh, it's a combustion because I see oxygen going in, carbon dioxide and water going out. If you ever forget, you can think, okay, we always use the word burn if we chemically burn our food. Well, what are you doing there? You're breathing oxygen in, all right, then the cells do their thing, and then you give off carbon dioxide and water vapor as a product. All right, so anytime you chemically burn something, that would be combustion. Okay. All right. We're going to do, actually, we've done a lot of combustion examples. In the lab that we're going to be doing this Friday, I don't think combustion is on there. You would think that burning the piece of magnesium would be combustion. Just because you use fire, it's not always a combustion. All right. So don't mistake that as being combustion. Let me give you an example they give on the note sheet. If you had this reaction, C10H8 plus 12O2, and this is a balanced equation, so that's where that 12 comes into play. It yields 10 molecules of CO2, or moles, plus 4 moles of water, H2O. All right, that would be considered a combustion because you have oxygen going in, and you have carbon dioxide and water as a product. So that's basically, how you classify a reaction as combustion. You just look at the reactant and you look at the product. Okay. Sometimes the question will come up: why does O have a 2 on it? There's 7 diatomic molecules that always travel in pairs. All right, and so I'll put these off to the side so you'll remember. This is the diatomic atoms. They always travel together. All right, there's a number of little mnemonic devices and ways to remember what those diatomic atoms are. There's phrases that you find on the internet and all. I made up my own phrase that helps me to remember. If you just remember no, like a play on words for K-N-O-W, like no, but N-O-H, no, nitrogen, oxygen, hydrogen, and then your halogens, all right? And they don't think that the last halogen on the group is diatomic, so you just go straight down: fluorine, chlorine, bromine, and iodine, all right? They all travel in pairs when they're isolated as a pure gas, all right? So that takes care of the question, why is there a 2 there, subscript 2? So those are your diatomic atoms. I'll be saying that a lot from here on out. So oxygen, if a nurse or doctor says, I need an O2 tank, that's why, or we need O2 over here, that's why they say O2, because oxygen's diatomic. It never travels by itself. It's always 2 atoms together, okay? All right, so combustion, you're chemically burning something, you're taking oxygen in and releasing carbon dioxide and water. And there's a ton of examples, but that's pretty much a classic example right there, because you got oxygen as a reactant, carbon dioxide, and water as products. All right, let's look at synthesis. All right, if you synthesize something, you're making something, right? So synthesis is bringing smaller compounds together. All right, and this is not on your paper, so you want to add it. Another name for synthesis is combination, because you're combining. Combination reaction. I'm going to again put RX in for reaction. Now, this is the first thing you're going to do in the lab, or it may not be the first thing, but it's one of the things you're going to do in lab tomorrow. All right, you're going to burn a piece of magnesium ribbon. So let's use that one as an example. If I take magnesium and I burn it, I bring oxygen to it, all right, in the atmosphere, and I heat it up. And oxygen, remember, is diatomic. I'm going to form, all right, I'm going to form magnesium oxide. So you may look at this initially and say, oh, oxygen's going in, it's a reactant, it must be combustion, right? No, this time, because you don't have carbon dioxide and water as products, you took two smaller compounds or elements and you join them together as one larger compound. That's called synthesis, all right? Combination or synthesis reaction. And it's synthesis because you're taking simple things and making something more complex, okay? So when two or more simple compounds combine to form a more complicated one, that would be combination or synthesis reaction. All right, let's look at decomposition, which is like the opposite. So decomposition, just like it sounds, you're decomposing something, you're breaking it apart. So if you had this reaction, they use a generic example here of compound AB yields A plus B. That's just to show you that something big is breaking into something smaller. Tomorrow in lab, we're going to take copper carbonate, CuCO3, put it in a test tube, heat it up. And again, just because you're heating something doesn't make it a combustion reaction necessarily, all right? And then we're going to test for the presence of carbon dioxide gas. Let me go ahead and balance this one out. Actually, it's already balanced just by the nature of it. 1 Cu, 3 oxygens, 1 carbon. Good. All right. So when we heat up this copper carbonate, it's going to be a green powder. Put it in a test tube, and you just simply add heat to the test tube. It's going to start kind of bubbling a little bit, and it may start to get a little black, the powder. All right. When you take a lit splint and you go into the mouth of the test tube and the splint blows out, that indicates the presence of carbon dioxide, all right? So you have something big breaking into two smaller somethings, right? So you gotta get used to seeing any equation or formula and identify it as one of the 6 types of reactions, all right? So don't get caught up in because you may see something you don't recognize. All right, this one, you know, it's on your lab sheet, right? What if you see another chemical equation that you've never seen before? How are you supposed to know it's decomposition? Something big breaking into 2 smaller parts. That's decomposition. So it's the opposite of synthesis. Rather than putting it together, you're breaking it up. All right, look at the 4th type of reaction, all right, which is single displacement. And sometimes you'll see the word replacement. So single displacement, all right? And they may refer to that as an SD reaction or a single replacement reaction, okay? All right, we've done this quite a bit when we generate hydrogen gas. All right, we took magnesium and dropped it into hydrochloric acid, and it formed magnesium chloride and hydrogen gas. All right, if you look at this very carefully, all right, this magnesium is the cation, it's the positive ion. Remember, it was 2 plus because it's an alkaline earth metal. This was attached to chlorine, so this was the other cation, but it got bumped. All right, so here we have magnesium by itself. Here we had hydrogen that was joined to chlorine, and suddenly things kind of switch partners, right? But only one thing switched. A lot of times, especially if you're going online, you'll see a little common example where it has a dance couple, all right? Here's a little dancer with no partner. That's supposed to be a little stick man on it. Then you have, I'll put a baseball cap on him. You have this scenario. So here's a little dance couple here. All right. All of a sudden, the cation, the positive ions, switch. So now you have this scenario, and then the cation that used to have a partner no longer has a partner. So it's like one single element has switched partners, and there's always somebody's always by themselves, right? All right, so that's what happens when we generate hydrogen gas by using magnesium and drop it into hydrochloric acid, and then it gave off the gas. We did that quite a few times for the Pringles can demo. We're going to do it for the hydrogen eggs. We're going to do it in lab and actually hear the hydrogen pop tomorrow in lab. So that's a common way that we generate hydrogen gas. Double displacement, you may hear it called, single displacement, you may hear it called single replacement, or you may see it designated as an SD reaction. All right, then there's a double displacement. So a fifth type of category is double displacement. And again, you can hear this called a DD reaction or a double replacement reaction. Excuse me. Double replacement. Okay. I usually say displacement, but you can say displacement or replacement. All right. Tomorrow we're going to do a double displacement when we take calcium chloride, CaCl2. We're going to put it into sodium carbonate, N2CO3, and then we're going to form salt, table salt, NaCl, and calcium carbonate. I'm going to go ahead again and balance these. They may already know it's not, so I'm going to put 2 there. 2 should be balanced. Okay. A double displacement will form what's called a precipitate. And tomorrow we're going to form this solid that's going to fall out of solution. That's called a precipitate. Calcium carbonate is going to be a real chalky white substance that when you take a clear liquid of solution of calcium chloride and you mix it with a clear solution of sodium carbonate, you mix them and all of a sudden you're going to get a white milky substance that kind of falls down the bottom of the test tube. All right, but that's called a double displacement. The easiest thing you can do to identify it is look at your cation, positive ion. That's the cation there, that's the cation there. Here's the cation here, here's the cation there, right? Because we know sodium, calcium, they're positives. They're on the left of the zigzag line of the periodic table, right? Here's a common analogy that you see all the time in books and on the internet. Now let's look at the dance partners where everybody's got a partner. I'm going to use a little top hat and hair like this. Kind of bear with me on my drawings. I know they're real basic. I'm going to put her hair up in a kind of a bun. All right. So here we go now. these two cations, if they switch partners, and you're left with top hat dude with the bun hair here, and then you're left with the baseball cap figure with the hair that's kind of down, all right? That would be an example of double displacement. So get used to seeing that when you have these two cations switch places, all right? And these two, they all get a new partner. So it's you know, ever how you want to look at it, but it's like this cation switches places with that cation, all right? That's called double displacement. All right, now the last and final type of reaction is acid-base. You need to understand that all acid-base reactions are types of double displacement, but not all double displacement reactions are acid-base. All right, it's kind of like saying, oh, all trucks are a type of vehicle, but not all vehicles are trucks, right? So, you know, all acid-base reactions are categorized as double displacement, but they're not, all double displacement are not an acid-base. So let's see what an acid-base looks like. All right, so an acid-base reaction, here's what how you can identify the sixth type of reaction, acid-base. All right, an acid-base reaction, there's a common phrase that says an acid plus a base forms a salt plus a water. So if you look at a double displacement reaction, you see a lot of, you know, two cations, two anions, and you know it's double displacement because things have switched, the cations have switched. If you see a salt and a water as a product, then that double displacement specifically is an acid base, all right? An acid by definition, a salt by definition is an ionic compound in chemistry where you have a cation and an anion joined together ionically. So there's lots of salts, okay? You're familiar with NaCl, table salt, but Ki, we use potassium iodide on occasion for as a catalyst to speed up reactions. That's a type of salt. KCl is a salt, all right? Na, sodium bromide, NaBr is a salt. So anytime you have a cation and an anion ionically joined, and they're usually on opposite ends of the periodic table, that would be a salt. All right, so don't think that salt just means NaCl. There's a ton of salts. So let's look at what they gave us. They gave us lead nitrate plus potassium iodide yields lead iodide plus potassium nitrate. All right? Because there's no water formed, I don't see a water, okay? This is a type of a double displacement, all right? But it's not acid-base. It's not an acid-base reaction, all right? So trying to get you to see that not all double displacements count as acid-base. All right, they did give us a specific acid-base reaction. If you had hydrogen bromide plus sodium hydroxide, we use sodium hydroxide for a lot of stuff too. That's a common base used in lab. All right, it yields sodium bromide plus water, okay? That would be a double displacement reaction that is an acid-base reaction. Okay, how do I know that? How do I know? Because I see where hydrogen and sodium kind of switched places, right? This hydrogen goes over to that hydroxide and joins the hydroxide. So we got two H's and one O. So when you have a hydrogen and a hydroxide coming together, that forms water. H plus plus a OH minus joined together as water. So when I see a water as one of my products in an acid-base reaction, all right, that's a giveaway that, oh, we're dealing with a double displacement reaction that specifically is acid-base. And sodium bromide, it's an ionic compound. It's a metal joined ionically to a non-metal, so therefore it's classified as a salt. So an acid plus a base yielding a salt plus a water, that would be an acid-base reaction. Now, depending on the source that you're looking at, a lot of times it may say, you may go online and it says the 5 types of chemical reactions. If you ever see that heading, they've lumped acid-base with double displacement. They're not separating it out, okay? So what I've done for you, I've shown you like specifically the 6 types of chemical reactions. Tomorrow in lab, we're actually going to demonstrate 4 types of chemical reactions, all right? We're going to look at synthesis reaction, decomposition reaction. We're going to look at a double displacement and a single displacement, all right? But those basically are your notes for how you identify a type of reaction. The best way to practice, I've uploaded an online quiz for you, and it regenerates different examples. So the more times you take that quiz, the easier and easier it becomes to identify different reactions. Just remember, if you see 2 cations that both have partners, right? If they both switch off, that's double displacement. If you ever see one cation that's kind of by itself, and then it's joined to it switches with another cation that was joined to an anion, that's single displacement. Use the dancer analogy, okay? If you have oxygen going in to a reaction and carbon dioxide and water coming out as products, then that would be combustion, all right? Anytime you have 2 simple molecules or compounds that combine and make a bigger compound, synthesis. The opposite of that, you can look at that as being the opposite. If you have a big compound, it breaks into simpler compounds or elements, that'd be decomposition. All right, remember that acid-base reactions are technically a type of double displacement, but not all double displacement reactions are acid-base. All right, to be an acid-base, it's going to yield a salt and a water. And then you know it's specifically an acid base. All right, there you have it, 6 types of chemical reactions.